Welcome back. We just talked about dynamic routing. We just talked about static routing, all of that kind of stuff. Now it's time to shift gears a little bit and think about high availability. Now, we lump in ECMP, or equal cost multipathing, to this HA model, this high availability model, because in a way, equal cost multipathing provides us some high availability for for our routing, for our north-south routing in a lot of respects. So we're going to kick off with ECMP and talk about what it is, right? ECMP basically allows us to take multiple paths upstream that cost the same, right? When we say cost, they cost from a routing perspective, that cost the same. And we can hash traffic to spread that north-south load across multiple uplink interfaces to multiple upstream peers. So, here in this diagram, I've got 4 uplinks, rather 4 peers. Ultimately, right, from edge 1, I can send traffic to top of rack left or top of rack right. From edge 2, I can send traffic to top of rack left or top of rack right. That's 4 paths that I can distribute my traffic across. And so equal cost multipathing allows us to take a flow and figure out which of these paths is ultimately going to be forwarded to. Now that's done through a simple 5-tuple hash, source destination, source port, destination port, and protocol. And, this allows us to kind of spread the load across those different paths that we have available. Now, turning on equal cost multipathing is really, really simple. Under my dynamic routing, whether we're looking at BGP or OSPF, we have an ECMP toggle, right? That tells NSX that if we have multiple equal cost upstream peers, that we can go ahead and hash that traffic across and get a benefit out of having multiple north-south traffic lanes. Here we see the toggle in OSPF, pretty much just like it was in BGP. And so that's really all there is with equal cost multipathing. It's either on or off. It's a pretty simple thing to configure. Now, from here, we're going to move into high availability. High availability gives us the configuration choice for our gateways and how they're going to behave inside of an edge cluster, right? Inside working with the multiple edge nodes that are members of an edge cluster. Now, my tier 0 gateways can be configured active-active or active standby. Now, active-active simply means that a number of edge nodes have active service routers instantiated on them. And that means that we have the ability to spread our north-south workload across multiple edge nodes, right? In order to use that equal cost multipathing we just talked about, I have to configure my gateway in an active-active mode. Now, the downside of that is that my active-active gateways don't support stateful services. So stateful NAT, stateful firewalls, things like that. Now, we'll talk in a much later video, about a new capability in NSX 4 that allows us to support stateful services on an active-active gateway. But we'll get into that when we start talking about services. Right now, we're just talking about the basic operating functions. So active-active simply means multiple edge nodes, multiple service routers ultimately are providing services, and that typically goes with stateless services, or I can configure my tier 0 gateway in an active standby mode to provide me a single active node and a single standby node and provide for stateful services rather. So stateful NAT, source NAT, destination NAT, stateful firewall. Active standby is the only real configuration in this context for our tier 1 gateways. So I have some thoughts about whether my tier 0 gateways are active-active or active standby, but my tier 1 gateways rather are really going to be active standby in nature. Now, we can drive traffic across multiple active service routers. This is our active-active mode where all of my service routers are active. All right. Here we make our note about stateful services on an active-active cluster. Again, details are going to come in the services the services series of videos. With BGP, for example, all of our gateways are going to be active. All of our service routers and the uplinks on those service routers will have active BGP peers upstream. The distributed router has a part in equal cost multipathing at this point because, well, when traffic gets to the tier 0 distributed router, it has multiple possible paths north, right? Multiple paths from the DR to the SR because I've got multiple SRs. So the distributed router has to make a decision, and it's going to use that same 5-tuple hash to figure out which of the active service routers we're going to forward the traffic to. Once the traffic gets to the service router, we have another ECMP hash to figure out which of the uplinks we're going to forward that traffic across. With OSPF, well, we really have the same thing going on. We're just using a different routing protocol. My distributed router figures out which of the service routers to forward to, and in turn, the service router figures out which of the upstream peers to forward the traffic out to the physical. Now, active standby, here I've got 2 edge nodes in my edge cluster. I've got an active service router on one edge node and a standby service router on another edge node. And this simplifies the synchronization of state between my gateways, or between my service routers more precisely. This gives me stateful firewall. This gives me source and destination NAT availability. This gives me my VPN capabilities that, again, we'll talk about in services. And so this gives us an easy way to synchronize the state from those services from an active processor to a standby processor, right? The service router being the processor in this case. Now, with dynamic routing, we've got to take a couple of things into account when we're thinking about the broader picture of active standby gateways, right? And you know, one of those things is that we can't forward traffic from a distributed router to the standby service router because the standby service router router link interface, or not router link, but intra-tier transit link interface is non-forwarding, right? It's essentially disconnected. Now, that doesn't mean that our uplinks are inactive, right? The uplinks on the active and the standby service router are still going to be active, which means that I have an active BGP peer from my active SR to my upstream router, and I have an active BGP peer from my standby service router to that same peer. Now, that means we're sending the same prefixes across 2 different paths, but we only want to send and receive traffic through our active path. Well, we're going to enable that by making the routes coming from the standby service router far less appealing to the routing protocol by appending the autonomous system number 3 times to each prefix. In effect, what that's telling BGP is that you can forward traffic to the standby service router to get to a destination subnet, but we're kind of going to run in circles a bunch of times before we can get there. Well, if I've got a choice where I can go directly to the destination, or I have to stop halfway and run laps around, around the field a few times before I can move on, I'm going to choose the more direct path, right? I'm going to choose the path where I'm not running laps around the field. And so that makes the standby service router advertisements far less desirable. They're not going to be installed in the upstream routing table, even though they're going to be available just in case. So we're going to set that. That means that traffic's only going to come into the active service router. And so even though both uplinks and both BGP peers are active, we're still only going to use the one of them, the one active. We're going to avoid the standby. A similar thing's going to happen with OSPF, although we don't have a concept of autonomous system prepend with OSPF. So what we're going to do from our standby peer in OSPF is we're simply going to advertise routes with an exceptionally high cost, 65,534. Right, that's the cost value. And that tells OSPF that we really want to avoid that because I would rather afford a cost of 20 than a cost of 65,000. Right? It simply makes the route to the active service router far more preferable And so that's the one we're going to use. Now, how do we figure out when to fail over if we're in an active standby configuration? Well, we have two basic mechanisms that we use to detect whether or not an edge is live. One of those is the state of the upstream peers, right? BGP or OSPF. What's my peer state? The other is going to be more of a southbound check where we're validating that we have connectivity across our management network, right? So from management interface to management interface on the edge, as well as from the overlay network. So essentially from tunnel endpoint to tunnel endpoint, we're sending bidirectional forwarding probes across the overlay network. Now, we have to lose both of these probes north or both of these probes south in order to trigger a failover response, right? Losing just one of them does not automatically mean that we have a failure. We have a failure, but it's not a failure to trigger a failover. So we've got to watch that. We've got to think about that. So why BFD? Well, bidirectional forwarding detection is a very lightweight protocol. It's a very low overhead protocol, and it's fast, and it allows us to detect that failure very, very quickly. With a virtual edge, we can detect that failure as quickly as 1.5 seconds. With a bare metal edge, we can detect that failure as quickly as 150 milliseconds, 150 milliseconds. So when I lose both of the BFD probes, then we'll trigger a failover response, and my active service router on an edge will fail over to the standby service router. The other failure detection is northbound. It's my peering, right? So if I lose all of my northbound peers from my active edge, that will trigger a failover, right? If I still have some northbound peer, right? If I've got two peers and I only lose one of them, that's not going to trigger a failover. I have to lose both of them in order to trigger the failover for my service router. Now, in an active standby HA mode, I have to figure out how I'm going to fail over, and more importantly, how I'm going to fail back, or if I'm going to fail back. And that's done by configuring my gateway in an active standby mode and then defining whether we are using preemptive or non-preemptive failover. The default is non-preemptive. What non-preemptive really means is that I just want the service to be up. I'm not so concerned about which service router is providing the service or which edge node that service router is on. So we're going to fail over and stay, right? That's what non-preemptive means. We're gonna fail over and we're gonna stay there when the former service router, the formerly active service router, returns to service. It's going to see that there's an active service router in place, and it's going to assume the standby role. Now, preemptive mode, by contrast, the non-default configuration says that I have a preferred location for this service to operate, and I want it to be there unless the preferred location is unavailable. And so what we'll do is in a failure, we'll fail over to the standby service router. And if we're in preemptive mode, when the formerly active service router returns, it's going to see that the service exists in a non-preferred location, and we will then preempt the service and fail it back to the previously active edge, right, to the previously active service router. So I've got my choice here. Do I want to automatically fail back to where the service was, or do I want to fail over once and just leave the service where it falls? You can make that choice based on your comfort level and your tolerance for that brief network interruption of the fail back. So that is a quick review of our failover modes and how HA works in NSX4. Like I said, we're going to get into the stateful active stuff a little bit later on. Be patient for that. For right now, active, and active standby are really the ways that we're going to think about things. So come back in the next video. We've got more cool routing stuff to talk about. We'll see you there.